Hello students, in this video we'll discuss the Cauchy estimates along with Liouville's theorem and extensions of Liouville's theorem. So what are the Cauchy estimates? So let's let f map omega into C be a holomorphic function. Okay, and suppose that DAR closure, there's a closed disk inside omega. Then what do we know? Then the Cauchy formula for the nth derivative, f n at a, gives what? Let's write down over here. Gives fn of a is n factorial over 2 pi I, the integral over C A R, the circle, right? And then f of zeta over zeta minus, in this case, a d zeta, like that. And so now, of course, what we want to do is we want to just parameterize this, right? So if we parameterize this, what do we get? We get n factorial over 2 pi I, the integral from 0 to 2 pi. And then I'll have a plus r I theta, so I'll have a f of a plus, in this case, r e to the I theta, right? Beautiful. Now, of course, the a will cancel out. I'm just going to get an r. Of course, this is to what power? I missed the power over here, just n plus 1, right? So I'm just going to have an r e to the I theta to the power n plus 1. And then I have an I r e to the I theta d theta over here. Okay? Good. And so now what's happening over here? So let's think about this carefully. So what will happen is that if I put absolute values everywhere, absolute value, absolute value, absolute value, absolute value, of course, and I bring the absolute value inside the integral by a triangle inequality, what will happen over here? I'm going to have an n factorial that's left over. This is less than or equal to n factorial, okay? Let's count the r's we have over here. So I have r to the n plus 1, r. So I have an r to the power n. That's the power of r. The modulus of e to the I theta is going to be 1, so all those moduli are going to cancel out. And then I have the integral of this thing, which I can't control over here. But what I'm going to say is I'm going to say this is less than or equal to the integral from 0 to 2 pi of just the maximum of the function f of z, where z is on CAR. Just the largest value can be d theta. When you plug in the maximum, there's nothing to integrate over there, so you're done, right? So good. And so now what does this give us? This automatically gives us the Cauchy estimate. So this implies that fn of a does not exceed n factorial over r to the n. And then I'm going to write like this. I'm going to say it's f, and they write L infinity for L infinity stands for maximum. The maximum over what set? Over the circle CAR over here. Okay, good. The largest it can be. Excellent. Okay, so these are the Cauchy estimates. Now, the Cauchy estimates are very valuable. Why so? Here's the classic example of using the Cauchy estimates. So we say, definition, f mapping C to C is entire if f prime exists, if f is holomorphic everywhere. At every point. Z in C. Okay. And so here's the first version of Liouville's theorem. Liouville's theorem says a bounded analytic function is constant. F mapping C to C, entire and bounded. So if I give you an entire function that's bounded, then f has to be constant. Then f is constant. Okay. How do you prove Liouville's theorem? It's fairly straightforward. So here's the proof. Proof. So for any point, so of course if f is entire, you can write like this. F of z is the sum and goes from 0 to infinity. It's entire, so its Taylor series at the origin is valid everywhere. Like that. Okay, beautiful. And now estimate Fn of 0. Okay, and so for any r, what can we say? We can say that f, let's do this. Let's just do fn. If we want to do fn, or we can just say f prime. Well, we can say f prime is 0 everywhere, but it's easier to do fn, right? So what's fn of 0? Well, it's no more than what? It's no more than n factorial over r to the n times the maximum over c0r of f of x, f of z. Okay? But we're assuming that f is bounded, so this is less than or equal to n factorial, and then times a constant m, that's just a fixed constant, over r to the n. Now, of course, this is true for any r. So this is force. This force is, as long as n is greater than 0, this goes to 0 if n is bigger than or equal to 1, right? Okay, so in other words, all the coefficients in this expansion are what? Are less than or equal to 0, so there's 0, which forces f of z, in this case. The only term in the Taylor expansion that it survives is just f of 0. So f of z is f of 0, and f is constant. That's the proof of Liouville's theorem, okay? Now, you can notice from this, you can say, well, wait a minute. Actually, if I give you some other estimates, instead of just being bounded, I can get a generalization of this. And so here's the generalization. So here's another proposition. I call this like Liouville 2. This is the general Liouville theorem. Okay. It says if f is entire, and f of z in modulus is less than or equal to z to the power n. Okay. In other words, I give you a bound. You can even put a constant if you want here, right? Less than or equal to c times z to the power n, like that. If it's bounded by the nth power of the modulus of z, then f is a polynomial of degree at most n. Okay? And the proof is exactly the same thing. Since f is entire, write down series expansion at the origin, and then estimate the nth derivative at the origin, right? So how would our estimate go over now? So now our estimate goes like this. Fn of 0, what do I have? I've used n, so let me do k now, right? Fk of 0, what's this going to be bigger than? Less than or equal to k factorial over r to the k, and then the max on c0r of f of z. But now what can we bound that by? We can say this is less than or equal to k factorial over r to the k, and then I'm going to have a constant c times r to the n, right? And so this goes to 0 if k is what? If k is strictly bigger than n, right? If k is strictly bigger than n, that goes to 0. So in other words, the terms in the expansion all go to 0 past the point n. So that says that f of z is what? Is f of 0 plus dot, 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 plus all the way down to f n of 0 over n factorial z to the n, right? Now, of course, some of these terms may be 0, but that says that exactly that f is a polynomial degree at most n over here. So the Cauchy estimates give you these excellent bounds. So if you have some uniform bounding an entire function, you're able to say a lot of information about that function by the Cauchy estimate. So in other words, it gives you even more of a rigid structure to the properties of holomorphic functions that are exhibited by these estimates that come exactly from the Cauchy integral formula. Thank you very much.